Welcome to our cosmic journey through the universe. Today, we're diving into one of the most fascinating and cataclysmic events in astrophysics: stellar collisions. Imagine a universe where immense forces collide, where stars, those massive, luminous orbs, meet in a spectacular clash. What happens when these celestial giants collide? How do such dramatic events shape the universe as we know it? Join us as we explore the extraordinary phenomena of stellar collisions and mergers, revealing the secrets of the cosmos that lie hidden in these cosmic explosions. To understand stellar collisions, we must first grasp the life cycle of stars. Stars are colossal celestial bodies formed from clouds of gas and dust, primarily hydrogen and helium. They shine brightly, converting hydrogen into helium through nuclear fusion in their cores, a process that releases tremendous energy. But stars are not solitary wanderers in the universe. Many exist in binary systems, two stars bound together by gravity, orbiting one another in a delicate dance. Over time, these stars can lose energy due to gravitational interactions and begin to spiral inward, drawn together by their mutual attraction. But what about encounters in crowded star clusters, where thousands of stars exist in close proximity? In these dense environments, gravitational interactions increase the likelihood of collisions. As stars approach one another, they can undergo interactions that lead to collisions, resulting in cataclysmic events that reshape their fates and the dynamics of the surrounding star systems. Let's delve deeper into the various types of stellar collisions that can occur and the phenomena they produce. There are several types of stellar collisions, each yielding its own spectacular outcomes. Binary star mergers. Picture two stars locked in a gravitational embrace, orbiting each other for eons, their fates intertwined. As they lose energy, they spiral closer together, ultimately merging into a single, more massive star. This merger can produce dramatic bursts of light, sometimes outshining entire galaxies. These luminous outbursts are not merely flashes. They can reveal the internal dynamics of the merging stars, giving astronomers a glimpse into the processes that govern stellar evolution. Supernova interactions. Massive stars live fast and die young, often culminating in a supernova explosion. When a massive star reaches the end of its life cycle, it can explode with unprecedented force, scattering its outer layers into space. The remnants of this explosion can collide with nearby stars, resulting in violent interactions. These interactions can strip away outer layers from other stars, reshaping them and creating new stellar structures. Moreover, the shock waves from the explosion can compress surrounding gas clouds, igniting the formation of new stars, thus continuing the cosmic cycle of life and death. Neutron star and black hole mergers. One of the most enigmatic collisions occurs when two neutron stars, or a neutron star, and a black hole collide. Neutron stars are incredibly dense remnants of supernova explosions, packed so tightly that a sugar cube-sized amount of material would weigh as much as a mountain. When they merge, the event is cataclysmic, releasing a colossal amount of energy and producing gravitational waves that ripple through space-time. The resulting collision can create gamma-ray bursts, some of the most energetic explosions in the universe, detected from billions of light-years away, providing us with invaluable data about the nature of these exotic objects. When two massive objects, such as neutron stars or black holes, collide, they generate ripples in space-time known as gravitational waves. This phenomenon was first predicted by Albert Einstein's theory of general relativity, a revolutionary idea that challenged our understanding of gravity and the universe. In 2015, The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting these elusive waves for the first time. This groundbreaking discovery not only confirmed Einstein's predictions, but also opened a new window into the cosmos. Gravitational waves carry information about their origins, offering insights into the properties of the colliding objects and the dynamics of their interactions. Imagine the excitement of astronomers as they sift through the data from LIGO, detecting the faint echoes of cosmic collisions that occurred millions or even billions of years ago. Each detection provides a unique snapshot of a violent event, revealing the secrets of the universe. Gravitational wave astronomy allows us to study phenomena that are invisible to traditional telescopes, providing a new perspective on the cosmos and deepening our understanding of the fundamental forces that shape our universe. The aftermath of stellar collisions can lead to a plethora of fascinating phenomena, each illuminating different aspects of cosmic evolution. Supernova remnants. After a massive star explodes in a supernova, it leaves behind a nebula, a stunning, expansive cloud of gas and dust. This nebula is more than just a beautiful cosmic painting. It serves as the birthplace of new stars. The shock waves generated by the supernova compress surrounding gas clouds, initiating the processes that lead to the birth of new stellar objects. Over time, these newly formed stars will join the ongoing cosmic dance, continuing the cycle of creation and destruction. Kilonova events. When two neutron stars collide, they create a kilonova, an explosion that, while less energetic than a supernova, is rich in heavy elements like gold and platinum. The collision disperses these elements into space, contributing to the cosmic chemical enrichment of the universe. As the kilonova fades, it leaves behind a remnant that may become a black hole or a more massive neutron star. These events are crucial for understanding the origins of heavy elements in the universe, and astronomers eagerly monitor them for insights into stellar evolution. Formation of exotic objects. Stellar mergers can also lead to the creation of exotic celestial objects. For instance, when neutron stars collide, they can result in the formation of magnetars, neutron stars with incredibly strong magnetic fields. These magnetars are fascinating objects that emit intense bursts of radiation and are some of the most magnetic entities in the universe. Additionally, when sufficiently massive stars merge, they can form black holes, warping space-time and creating gravitational wells that can capture anything that ventures too close. Stellar collisions have far-reaching implications that extend beyond the individual stars involved. These cosmic events play a crucial role in the broader context of galactic evolution. The energy released during these dramatic interactions can trigger new star formation in nearby regions. For example, the shock waves produced by a supernova can compress surrounding gas clouds, igniting the birth of new stars amidst the chaos. In densely populated star clusters, the merging of stars can lead to complex interactions that reshape the environment. The gravitational forces at play can alter the trajectories of nearby stars, influencing their fates and contributing to the dynamic dance of the galaxy. The cycle of stellar births and deaths creates a rich tapestry of matter, where the remnants of old stars feed the formation of new ones. This cosmic recycling process is a reminder of the interconnectedness of the universe. Every stellar event, be it a violent collision or a gentle birth, contributes to the ongoing evolution of galaxies, enriching the cosmic environment and facilitating the emergence of new celestial wonders. In conclusion, stellar collisions are not merely catastrophic events. They are fundamental processes that shape the universe in profound ways. From the explosive birth of new stars to the creation of heavy elements essential for life as we know it, these cosmic collisions remind us of the dynamic and ever-evolving nature of our universe.